Continue on the testing issue. What I mentioned last week is a test example. The chip already manufactured. Is the chip. We want to test the chip to make sure that there's no manufacturing defect. The chip works correctly, right? And if it fails, then we will store it into the garbage can. They should not be sold to the customer. So how do you test it? How do you know this chip gives you the correct response? Given the input, you get the correct output and why? How do you know? Well, we try to feed some input pattern and look at the output whether or not it's correct, right? So given that we try to emulate, we try to test all the cases, how many input patterns do you need to test the whole chip? Every case should be tested. How many patterns for the input? Totally? It's a 4 input, 1 output chip. And given 4 input, totally you need 224 pattern. That's 16 input data, right? If you go through 16, then you make sure that the chip correct or not. But that's not going to be an easy job because a lot of chips will have much larger number the pin. Let's say you have 32 input and maybe 16 output. Given this kind of chip, it's going to be very, very complex to test, right? Even though it's a purely a combinatorial circuit, you have to test 2 to 3 second pattern. That's a huge number. And we know that testing equipment is very, very expensive. You should try to reduce, you should try to shorten the amount of time for the testing of the chip. Okay? So our job is try to reduce the testing time. And take that example, given 16 pattern, we are not too happy with the amount of the number of input pattern. But how do you reduce that input pattern? Then that comes up the form model. We assume that if the chip is failed, if the chip failed, must be some signal point stop at either 0 or 1. That's the form model. 我们假设这今天之所以会不 work， 是因为有某个讯号点被黏住了，被接到了 EDD 跟 ground， 这叫 stop at fault model。That's not all the cases， 这不是全部所有的可能，但是只光是纯粹测这一部分就足够涵盖非常非常高的它的可能是错误的在里面。因为即便别的原因发生的错误，它呈现的行为也是跟这个是一样的行为，所以我要测试这些东西，其实就足够可以测它的好坏。Alright, so for example, for A3 is one of the input. How do you know this chip, if the chip has a stop at 1 fault in A3? How do you know that? How do you test it? We feed 0110. Why? For input 0110, we should tell if there's a stop at 1 fault in A3, then the chip will not pass the test. Why is that? Because if A3 stops at 1, this signal will not give you 0. Instead, it's going to be 1. right? I mentioned before, VDD and ground are power wave. They have the strongest signal. They are the strongest signal in the chip. They have very, very huge driving power. It can override the other signal. Although you also give it 0, but because it's connected to VDD, VDD is much stronger than this signal, input signal. So you'll get 1 in input here, right? And then what the value in the output or the gate? 1, 0. So what the value for N1? You get what? 0, right? However, if there's no stuck at 1 fault, the original control value should be what? Should be 1, right? The correct original value should be 1, but if you are stuck at 1 fault here, you're going to get 0. Okay? And then what? In the bottom, you get 0 here, then you get 1 here. Okay. So what will be the value and y for original and for actual value if there is such one fault here? The original and correct value should be what? Should be 0, right? However, you are going to get 1 because of stuck one fault. And then we can tell that given input 0, 1, 1, 0, if you are getting 1, you know that this chip must be wrong, right? Because given 0, 1, 1, 0, if the circuit totally correct, you should get 0. However, if they stuck at 1 fault at this point, S3, you will not get the correct 0 value, but you will get it 1. Then you can distinguish, you can tell this chip failed the test, right? Must be something wrong with the chip. Maybe the other problem might not be this problem. Fine. If it's wrong, it's wrong. The chip must be failed. Must be faulty. Okay. So likewise, you can try to provide some specific indicator that can tell whether or not you can pass the stuff at 4. Alright? Let me repeat it. The reason why we give 0, 1, 1, 0 is we try to provide some pattern that can tell the output normal or abnormal, correct or incorrect, right? If you give 0, 1, 1, 0, the correct value should be 0 here, but if there's a stuck 1 fault, you get 1. Originally, it should be 1, but you're getting 0. Originally, you should get 0, but you get 1 if there's a stuck 1 fault. So you can tell whether or not the chip has the test. And this is not the only input pattern, right? How about this? Maybe but in this case, this is the only factor. Let me give another example. Last week we look at N1. Look here. Let's try to do that in reverse direction. Given that we want to test N1 whether or not it has a stuck at 1 fault, what should you give for the input? We are checking, we are testing whether or not there is a stuck at 1 fault at N1. So what should be the value you provide for the input vector? How do you get that? How do you reason about it? How do you derive from the problem? Here the thinking process. You want to test N1, start N1. You should try to give what? Try to give 0 here. That way, if they start at 1, 4 here, it's going to change it from 0 to 1, right? That's the only way you can distinguish. If you give 1 here, there's no way you can tell they start at 1, 4. Right? Let's say if you give 0, 1, you will never tell they start at 1, 4 here. Because the original value is 1. And if they start at 1, 4, you're getting the same value. You cannot identify, you cannot distinguish. So the idea is that you should try to provide a input vector that can distinguish correct, incorrect. So what should be the value here? It should be 1, 1. Because given 1, 1, you're getting 0. However, if let us start at 1, 4, you're getting 1. Right? How about the bottom half? What should be the value? The idea that we are trying to provide 1 here, such that the signal will get 1. Originally, 0 is correct value, 0 and 1. You're getting 1 out of 1. Right? However, if they start at 1, 4 here, you're getting 1. And 1, 1, you're getting 0. That way you can distinguish. If you don't provide 1 here, but you provide 0 here, there's no way you can tell. Because if 0 here, the output must be what? Must be 0, always. Right? Again, 0 here, you're getting 0. Invert, you're getting 1. It's going to cover that problem. Okay? So you have to give 1. Such that 1 here, 0, you're getting 1. 1 here, you're getting 0 in the output. That way you can distinguish 2 different values. Which one is correct, which one is incorrect. And in order to produce 1 here and N3, so we try to derive in the opposite direction. Then what? This has to be 0, this has to be 0, this has to be 1. Right? You want to get 1 here. The input for a NOR gate must be 0, 0. Then it must be 1. So 1, 1, 1, 0 is the input pattern to test start at 1, 4 and end 1. Is that clear? So basically, you can view like this. This is a problem path. That's the path we want to test. And this path is supported, the support path to support that we can distinguish correct or not. Any questions so far? 有问题？对目前这个需要用中文再讲一遍吗 ？Anyone？ 我需要用中文再讲一遍吗？不用方法。 How about start at 0? I'm going to move it. Start at 0. How do you test it? Again, N1. Start at 0, 4. So what I'm going to do? You want to test it? Then you should try to generate a 1 signal here, right? That's the starting point. You should get it 1, such that start at 0, 4 will force it to 0, right? That way you can distinguish it. Eventually get the output. And so the input for A3, A2 should be what? 0, 0, 0, 1 should be fine. 1, 0, either one should be okay. 0, 0, 0, 1, 1, 0. Either one should be okay. How about the 1.5? Well, that should be the same from the last example. You should provide 1 here, such that you are going to have correct value 0, 40 value should be 1. And again, like this. This is the support signal such that this signal can go through the output, giving you 2 different values. If you provide 0 here, there's no way you can distinguish. Okay. So in here it takes 0, 1, 1, 0. 0, 1, 1, 0. Well, why 0, 1, 1, 0 is preferred to the other two? Because in the other cases, we also have 0, 1, 1, 0. They are the same input pattern, which is good because one pattern you can provide more than one cases. 我只要给一个 input pattern 010，一次可以测好几个 case， 这样可以降低 ，you can reduce your testing time. The minimum number of the test pattern, which should be the best. Alright, the final example. Let's try N3, right? N3. N3. Start at 1 port. Okay, start at 0. How do you test it? We are doing this. We want to know that if there is not a 0 port at this point, the chip will not pass the test, even some specific input pattern. We can view, we can look at the output, we can tell, no, this is not a correct value, this chip must be wrong. So, what is the derivation for the input? But I said, we want to test start at 0, 4. You try to generate 1 at that point, right? You want to get 1 here. That way, you can tell whether or not something wrong. To get 1, then it should be 0, should be 0, should be 1 here. Alright? And for the N1, it has to be 1. For AND gate or NAND gate, this signal is a control signal. The control signal 1 for AND gate, then the input, this input is going to get through to the Y. AND gate or NAND gate, you should give 1 here. For OR gate or NOR gate, you should give 0. Equal several gate, give 0. Well, actually, we don't have to consider equals no gain. For n gain, the supported signal should be 1. For O gain or no gain, the supported signal should be 0, such that the other input will get through to the output. If there's a bubble here, then it will get inverse. Okay. So in this case, it has to be 1. And then it could be 0, 0, 0, 1, 1, 0. So 3 pattern can test the NC start at 0 fault. And here it should 0, 1, 1, 0, middle one. Because we already have 0, 1, 1, 0 in many places, which is good. We want to reduce the number of the pattern. There are quite a few 0, 1, 1, 0. Simply 0, 1, 0 can take 1, 2, 3, 4, 5, 6, 7. 7 cases. 7 start at fault. And then the minimum set, we have 1, 2, 3, 4, 5, 6, total 6 patterns. Much lower than 16, right? You don't need to take all 16 cases. 6 patterns should be enough to test the chip. Any question? Maybe you don't think it's too much different, but if the input number is more than that, like 20, 30 signals, then the dip is going to be huge. Okay, a large gap between the two numbers. Okay. Any question? Now, testing computer circuit is easy, actually, relatively. It's relatively easy to test computer circuit, especially for not too many input. That should be easy. And how easy for testing the circuit? We have two issues. Let's go back a little bit. There's a two terms, observability and controllability. We hope that the design, the circuit, has very good observability and very good controllability. That would make the testing much easier. Observability means ease of observing a node by watching external output pin of the chip. What I mean? It means how easy you can look at the output Y and you know that some internal signal is wrong. In this case, it's very, very good observability. 我们很容易观察出来，它讯号点有没有错，只要从 output 端看，就可以判断里面讯号有错误，这是可以做得到的。就我们给 pattern 一样 ，like we give some specific pattern, then we can easily tell output is wrong because of some start at fault, right? So this gives you very, very good observability. The other issue, controllability. The ease of forcing the node to 0 or 1 by primary input pin of the chip. Meaning how easy for us to provide specific input pattern that can force some internal signal to be 1 or 0. 它是不是很容易的可以从 input 端给一个 pattern， 使得内部的那个讯号点可以强迫它为零或为一，或使得它为零或一，我们可以很容易操控它。 因为这样子我才能够去测它。So, for chip to have good, easy or not for testing, that depends on your capability and observability. Typically, a conventional circuit has good observability and controllability. But for sequential circuit, that's going to be hard. That's going to be not easy. Conventional logic is usually easy to observe and control. Why? Provide some pattern, you can force some signal point to be 0 or 1. And you can look at the output, we can reason that something wrong with some point in the inside, right? And final state machine or sequential machine can be very difficult, requiring many clock cycles to enter desired state. It's not easy to drive some signal point to be 0 or 1 because it might go through 100 or 1,000 clock cycles to get that point. Especially the chip very complex. Especially state transition diagram is not known to the test engineer. Any question? So test pattern generation, this we take the test pattern. And this is a test pattern. So test pattern generation is important. Manufacturing test ideally will check every node in the circuit to prove it is not stuck at one of the row. And we try to apply the smallest sequence of test vectors necessary to prove each node is not stuck. Start 1, start 0. Like this, right? And this example. We need only 6 patterns. Good observability and controllability reduces number of test vectors required for manufacturing test. It's going to reduce the cost of testing because test time is very expensive, very precious. And later on, we're going to talk about design for test or design for testability. We can modify the design, adding some more circuit that will help you testing your chip. Any questions? Design for test. Definition of design for test is we design a chip to increase observability and controllability. Make it easier to test. Right? You might need some more circuit to help that. If each register could be observed and controlled, test problem reduces to testing conventional logic between registers. What does it mean? Let's say the chip very simple. Let's say this is the chip you design. There are 3 registers. There are 2 conventional circuits. More than 1 input pin and more than 1 output pin. So just a simple common circuit. And we say that the reason why sequential circuit is not used to test is you can flip-flop, you can register. If we can observe and control this register, this flip-flop, then the testing becoming easier because we only need to test the conventional circuit between different stages. It's going to reduce to testing conventional logic between registers, right? if we are sure that these registers are correct, these registers can be set to some specific value, they can be observed from the outside. So better yet, logic block to enter test mode where they generate test pattern and report the result automatically. It means that we can try to put some testing circuit inside the chip. This small testing circuit, and we can set the whole circuit in test mode where that testing circuit can generate test pattern. The test pattern is provided internally. They can automatically generate test pattern for the testing of the chip. And look at the output, we can report the result. This small circuit can try to gather the output value and make sure that you play the test, the chip plays the test. It's some kind of self-test. The chip can test itself, by itself. Because there's a circuit inside, it can generate the test pattern, it can look at the output and report whether or not it passed. And to do that, there's a very important technique which is called scan chain. We use scan chain to increase the observability and controllability. We try to modify each flip-flop in the chip to this. There's a 2-to-1 multiplexer for the input. Okay? D is the original input data. SI is the scan in. Okay, this is the scan in. This signal is scan, control signal, scan. Clock signal, Q output. Modify each flip-flop to this. Originally, should look like this. Clock. Q, E. That's it. We change all the flip-flops to the new design, including the multiplexer. And then the swing stage, the circuit will become this. Every flip-flop is going to be chained together. 所有里面的 flip-flop 都会被串成一串。Just like a string of pearl， 串成珍珠一样。每一个 flip-flop, every flip-flop is going to receive 2 input, either one, either the original data input or scan in. Only one of them will enter the flip-flop. And the output, one goes through the combination circuit, the other one will connect to the input of the next flip-flop. So before, 4 flip-flop, input 4 bit goes through combination circuit, 4 bit enter the 4 flip-flop and coming out through the combination circuit and entering the 4 flip-flop and coming out. That's the original circuit. But we modify each flip-flop to this. And then they can be chained together. Here will be input here, here will be input here, and here. And the output of here will go to the input of the next flip-flop. So it's just like a chain. From here, and here, and here, and coming out. So in the test mode, scan mode, we are choosing one, we are choosing this. The scan is 1, then you are choosing SI. When scan is 0, you are choosing D. So when the scan mode, every flip-flop, you are choosing this input. Okay, like this. Then what? You can see that the scan in connect like this. Get in, come in. It chain together. Coming out. When this control signal scan is 1, you're choosing this input. So the signal from the outside will be shipped into the chain of the flip-flop, one step after one step. And if you are trying to enter some sequence like this, 0, 1, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, so on and so forth. Each clock cycle, 1 bit is going to ship in, right? After one clock cycle, 0 comes in. Next clock cycle, 0 will shift it to here. And 1 will shift it up here. Right? After 2 clock cycle. Another clock cycle, this 0 will be here, this 1 will be here, and this 1 will be here. So on and so forth. So after 12 clock cycle, you have totally 12 flip-flop, and they are chained together. After 12 clock cycle, the 12 bit already in these 12 flip-flop. Is that right? This way, you can set each flip-flop, each register to be to have some certain value. We load, we load value into these 3 registers like this. After 12 clock cycle, we have already loaded 3 registers with specific value. 所以我们经过周期之后，我可以设定每一个 flip-flop 的值是多少。经过12个 clock cycle， 它一个一个一直往前推进，一直去 shift， 那就可以设定每一个我们所想要特定的值。We can make each register have the specific value we want to set. Right? After that, scan mode it change to become regular mode, normal mode, or regular mode. After we have already set up the value after 12 clock cycle, let's say, I don't know, but anyway, 0, 1, 1, 0, something like that, and 1, 0, 1, 0, and 0, 0, 0, 1, okay, for example. After 12 clock cycle, we have already set up the value we want to set. If you provide from scan in 0, 1, 1, 0, 1, 0, 1, 0, 0, 0, 0, 1, 12 bit input, right? After that, we change the mode to normal mode. Now it's 0, the normal mode. Normal, it becomes disconnection, right? Well, actually, you can see that we don't really need this 4 bit because after 1 clock cycle in normal mode, these 4 bits are going to be overwritten. So actually, you don't really need 12 bits, only 8 bits should be enough. Okay. Only 8 bits should be enough. So what we're doing here, we want to run for one clock cycle, just one clock cycle. After one clock cycle, 0, 1, 0, 1, we'll go through the logic cloud, the computer circuit, and getting the data left in this 4-bit register, right? Likewise, 1, 0, 0, 0 will be input of this logic cloud, computer circuit. And after one clock cycle, the new value will be left in this 4-bit register. 经过一个 clock cycle， 我这个值就通过它产生新的值被写在这边。同样时间，这4个 bit 通过这个5个电路写在这边。Right? Let's say after one clock cycle, you're getting 1, 0, 1, 0, 0, 1, 1, 1, for example. And we don't have to look at this because after one clock cycle, for the moment, we only consider about this 8-bit value. After that, we change it back to scan mode again. Now, it's becoming scan mode. Change to scan mode, and after 8 clock cycle, this 8-bit would be shooted out, the output here, scan out here, right? After one clock cycle, this one coming out, and this bit 1 will be here. This 1 bit will be here. 0 will be here. 0 will be here. 1 will be here. 0 will be here. 1 will be here, right? So after 8 clock cycle, you are extracting, you're getting 8-bit from the inside. So in the first scan mode, we are entering the data, we are set up data. And we run one clock cycle for normal mode. After that, we switch back to scan mode. We are getting all the internal value to the outside and look at the value. The first phase is control. The last phase is observe in the output, right? That way we can make testing the square circuit much easier. Okay, let's take a break.